Hello everyone, I'm Ronald Lane. This presentation of Understanding Sulfur Use in Agricultural Pest Control was put together to provide you with information that you need to know because you're not going to find it on most pesticide labels and safety data sheets for sulfur. Sulfur is an element represented in the periodic table by the letter S. The atomic weight tells you how much 1 mole of an element weighs in grams. 1 mole of anything is a very large number that's known as Avogadro's number. The atomic weight of sulfur is 32. This means that 1 mole of sulfur weighs 32 grams. Let's talk about something you're more familiar with, water. Why? Because understanding the phases of water can teach us about the phases of sulfur. Water is composed of 1 oxygen atom and 2 hydrogen atoms. The atomic weight of an oxygen atom is 16, and the atomic weight of a hydrogen atom is 1. So the atomic weight of water is 18 from the atomic weight of 1 oxygen atom plus 2 hydrogen atoms. Water exists in 3 different phases. Water vapor is a gas. Water ice is a solid. And water is also a liquid. When something goes from a solid directly to a gas, that process is called sublimation. The temperature of the air and of the ice are 2 of several factors affecting the rate of sublimation. With all other factors being equal, increasing the temperature of water ice from minus 50 degrees Celsius to minus 5 degrees Celsius will increase the rate of sublimations by thousands of times. 50 degrees Celsius is very cold. If the ice is broken up to increase its surface area by a factor of 100, the rate of water vapor formed by sublimation increases by a factor of 100. Ice is the solid phase of water. At temperatures below 32 degrees Fahrenheit, liquid water will turn to ice. Liquid water is the most abundant form of water on Earth. Water vapor will form from liquid ice more rapidly than from ice through a process called evaporation. You're familiar with evaporation from having water on your skin turn directly to water vapor. That process cools your skin because it takes heat from the surrounding environment. Sulfur also exists as a solid, liquid, and a gas. The freezing melting temperature of sulfur is 239.38 degrees Fahrenheit. Sulfur can sublimate from a solid to sulfur vapor and to a lesser extent go directly to sulfur dioxide. Sulfur vapor and sulfur dioxide also form directly from the liquid phase of sulfur. Roy Tucker of the University of California, Berkeley, laid the groundwork of our understanding of sulfur sublimation at ambient temperatures. Ultraviolet light, also known as UV light, also increases the efficiency of sulfur sublimation, and especially the oxidation of sulfur vapor to sulfur dioxide. And this is verified in a number of published studies. Sulfur vapor is predominantly 8 sulfur atoms bound together in a crown-like ring pattern. This is a gas. This diagram illustrates a lot of what's going on with sulfur in the environment. So you can see that sulfur is actually converting via sublimation into two different gases. One is sulfur vapor that you see coming off the left-hand side of both the cube and the molten liquid sulfur. And to the right, you see that sulfur is reacting directly with oxygen to form sulfur dioxide gas. The pathway to the left, to the sulfur vapor, is by far and away what is happening the most. And ultraviolet light from the sun increases the rate of sublimation, whether it's directly to sulfur dioxide gas or the more prevalent pathway to sulfur vapor. Sulfur vapor ultimately gets converted by ultraviolet light and oxygen into sulfur dioxide gas. Now, there are some pollutants that can convert sulfur vapor directly to sulfur dioxide gas, such as ozone, where ultraviolet light then is not required. But in general, in the absence of pollutants, sulfur vapor requires sunlight to convert to sulfur dioxide gas. Now, sublimation in agriculture does not occur at a rapid enough rate unless temperatures are above 68 degrees Fahrenheit. Like water, the rates of sulfur sublimation and evaporation increase with temperature. Melting sulfur in greenhouses was once a common practice for generating sulfur vapor to control pests in greenhouses. Solid sulfur is the common form of sulfur used in agriculture today. How does it behave following a pesticide application? We've already talked about that in the diagram just a little bit, but we're going to learn more. Application rate of 10 pounds of sulfur per acre is a common rate used for controlling pests and pathogens of grapes. A 10-pound cube of sulfur has a surface area of 0.1012 meters squared. The rate of sulfur sublimation from the cube is way too slow to provide any degree of pest control. When used as a pesticide, sulfur is generally milled into a fine powder of 44 microns or less, which creates an average particle size of around 15 microns. Milling sulfur to a dust increases the surface area by close to 9,000 times, increasing the rate of sulfur sublimation by a similar factor. If this 10 pounds of sulfur dust were suspended in the air for 72 hours, dispersed so that oxygen is around every particle, and it's suspended there for 72 hours in total darkness at 25 degrees Celsius, we would find that only 243 grams of solid sulfur remain, with 4,276 grams of sulfur vapor produced and only 17 grams of sulfur dioxide produced. Over 90% of the original mass has sublimated to sulfur vapor, and less than 1% has sublimated to sulfur dioxide. Now, let's suspend this mass of sulfur in sunlight for 72 hours at 25 degrees Celsius. No solid sulfur remains, and 5,444 grams of sulfur dioxide is created, which is 120% greater than the original mass of sulfur. 1,814 grams of sulfur vapor also remains. Under these conditions, the remaining sulfur vapor would convert to sulfur dioxide within another 4 days. The mass of sulfur dioxide generated is ultimately twice the mass of sulfur applied because of the attached oxygen atoms. Over 300 times more sulfur dioxide was generated with the addition of ultraviolet light from the sun than when sulfur particles were in total darkness. Let's go back to the massive sulfur dust suspended in the air in total darkness, and let's raise the temperature from 25 degrees C to 35 degrees C and see what happens. This increases the sublimation rate by 6.6 times. All of the sulfur sublimates to vapor in 11 and a half hours. And because of no sunlight, over 99% of that vapor is sulfur vapor and not sulfur dioxide. Temperature greatly impacts the decision to use sulfur in agriculture. Many sulfur dusting wettable powder pesticide labels instruct applicators not to apply when temperatures will remain below 68 degrees Fahrenheit. Why? Because sulfur is not a pesticide. Elemental sulfur has no documented mode of action for controlling pests, any pest. Sulfur must become something else to have any pesticidal activity. That something else is predominantly sulfur dioxide. Sulfur dioxide is the real active ingredient in a sulfur application. To a lesser amount, some sulfur can react with water to form sulfuric acid, which also has biocidal activity against life forms. Sulfur applications generate sulfur dioxide over time. This is through sublimation to sulfur vapor, which gets oxidized with air, oxygen in the air, and UV light from the sun into sulfur dioxide, and directly sublimating to sulfur dioxide. Sulfur dioxide is the real active ingredient in dusting sulfur and wettable sulfur powders. Applications of sulfur are ineffective at temperature below 68 degrees Fahrenheit because sublimation leading to sulfur dioxide is either not occurring or occurring at too low of a rate to be effective. As temperatures rise, the rate of sulfur sublimation increases exponentially. Many sulfur dusting spray labels warn to not apply sulfur to grape vineyards when temperatures will be above 90 degrees Fahrenheit and provide even lower maximum temperatures for applications to other crops. The University of California Integrated Pest Management website, in their section on modeling powdery mildew of grapes, there it states, under high temperature conditions, the amount of sulfur applied per acre should be reduced to avoid excess leaf burn. If possible, sulfur should be applied in the evening after temperatures drop below 90 degrees Fahrenheit to allow slow oxidation during the night, thus avoiding some leaf burn which occurs during the hotter daytime hours. Let's summarize what we have covered so far. Like water, sulfur can exist in three phases: as a liquid, as a gas, and as a solid. Like water, sulfur can sublimate directly from a solid to a gas. In the case of sulfur, we're looking at sulfur vapor and sulfur dioxide as the two gases. The rate of sulfur sublimation is temperature dependent, with the temperature being too low at 68 degrees Fahrenheit and below to provide effective control against agricultural pests and pathogens, and applications at temperature above 90 degrees Fahrenheit, risking damage to grapes. Ultraviolet light and sunlight is needed to effectively oxidize sulfur vapor to sulfur dioxide, which is another reason to apply sulfur at night during warmer weather. Sulfur acquires pesticide activity by oxidizing to something else, sulfur dioxide. Let's get more realistic with our model, and let's add in relative humidity. Relative humidity is another important factor to consider. A thin moisture film can form on dust particles at a high relative humidity, which inhibits the rate of sublimation. At above 90% relative humidity, sulfur sublimation can be reduced by 50 to 70% compared to dry air at the same temperature. Sulfur particles applied either as a dust or a dust in a wettable powder sprayed on a crop aren't going to be suspended in the air. They're going to deposit on leaf, soil, and other surfaces. Those particles would be subject to diurnal changes in temperature and sunlight and other environmental effects. Sulfur dust settling on surfaces and layering could easily reduce the surface area of sulfur exposed to the air by 50%, which would decrease the rate of sublimation by a like amount. Diurnal effects are going on. Sulfur particles are not constantly dark or constantly sunlit. The day lengths change. So, a sulfur application made in March is going to be in the daylight for a shorter duration than a sulfur application made in August. Temperatures at night are generally cooler than temperatures during the day. The relative humidity at night is generally higher than during the day. So these are all factors that have to be taken into consideration when trying to calculate how much sulfur would sublimate over a given period of time in an agricultural field. Along with environmental effects, there are canopy effects. The canopy affects the environment. A dense canopy increases shading of sulfur, and it also increases the humidity surrounding the particles within the canopy. Transpiration from the canopy has a cooling effect on the air. This all has an effect of reducing the rates of sublimation and oxidation to sulfur dioxide. Sulfur is heavier than air, so these sulfur gases tend to sink towards low spots like valleys, basins, or depressions. Note that air movement, such as convection and heating, can easily override pure density effects. The terrain affects how sulfur dioxide and sulfur vapor will spread in a field. In flat terrain, you get a relatively even spread of sulfur dispersing from the field and within the field, unless it's disturbed by wind or thermal convection. Note that small irregularities, rows, and plants can trap localized plumes of sulfur vapor. So we know that sulfur is heavier than air. So if it's not disturbed by wind or convection, it's going to pool and accumulate in low areas, leading to higher temperatures at ground level and in these low areas. This is especially true at night when air cools and sinks. And so air itself, everything is draining towards low spots. With sulfur applied to sites on hills or ridges, sulfur dioxide and sulfur vapor will generally roll downhill, but it can be dispersed upward by warm updrafts. The slope orientation, depending on whether the slope is hit by the sun and warmed to create these convection currents, or if it's shaded, have a big effect on convection. Fields that are terraced into hills can get layered accumulation where that trap sulfur dioxide and sulfur vapor in individual steps, especially at night. This type of layered inversions is really only possible if there's no air mixing. And in the absence of wind, sulfur dioxide concentrations in a field can build over the course of several days following an application. Also thins a boundary layer of sulfur vapor that surrounds sulfur particles, and this increases the rate of sulfur sublimation. A light breeze can overcome the tendency of sulfur gases sinking and disperse them from fields and low spots. Levels of sulfur dioxide would we expect to find in sulfur-treated fields in the days following an application? Based upon the physics of how sulfur behaves under different real-world environmental conditions, sulfur has the capacity to generate sulfur dioxide to concentrations harmful to humans and treated crops at common application rates. Have you ever smelled sulfur in a field following a sulfur application? Actually, no, you haven't. Sulfur and sulfur vapor are both odorless. Sulfur dioxide smells like a burnt match, and most people can detect it at concentrations of between 0.3 and 1 part per million. This detection limit of our noses is slightly below occupational exposure limits established by OSHA, NIOSH, and Cal-OSHA, which limits worker exposure to 2 to 5 parts per million over an 8 to 10 hour work shift. If you are unable to detect that burnt match smell of sulfur dioxide in a field, it is probably safe to work in that sulfur-treated field. Still, you must follow re-entry restrictions on the label. Exposure limits are set lower for public health and sensitive groups. The US EPA has a 1-hour exposure limit at 0.75 parts per million for children. WHO has a 24-hour guideline of 0.0076 parts per million of exposure. Cal OEHHA has a 1-hour exposure limit set at 0.09 parts per million. These exposure limits are below what humans are capable of smelling. California includes sulfur dioxide on its Proposition 65 list as a substance known by the state to cause reproductive harm in humans. This document is easily found on search engines and can be downloaded. I recommend that if you do download this document, that you at least read the executive summary. It does have credibility. Study cites studies showing reduced male and female fertility from exposures to as low as 0.015 parts per million to sulfur dioxide. It also cites many studies attributing miscarriages, premature births, and an assortment of birth defects to levels of sulfur dioxide exposure well below the detection capability of human smell. We can estimate levels of sulfur dioxide in ag fields by knowing concentrations necessary to provide pest control. Field studies are lacking, but a study by Yokoyama et al. Investigated the effect of low temperature storage combined with slow release sulfur dioxide pads on various pests, including spider mites in packed table grapes. The sulfur dioxide concentrations within the storage container ranged from between 0.2 and 1.6 parts per million over periods of 1 to 8 weeks. Notably, the study reported 98% mortality of Pacific spider mites and 99.6% for two-spotted spider mites after a 6-week exposure. Studies on using sulfur dioxide in the field to control fungal pathogens are either very hard to find or don't exist. Sulfur dioxide applied directly as a gas is too dangerous to even consider for field use. So that's probably why we don't have those studies. Sulfur dioxide is, though, used as a post-harvest treatment in contained storage at rates of 200 to 300 parts per million. These are generally fairly brief exposures of just an hour or two. Such concentrations are an immediate threat to human life. We can also estimate levels of sulfur dioxide in ag fields by levels that cause phytotoxicity. Those studies are actually available. From published literature, levels of 0.5 parts per million of continuous exposure are generally required to cause phytotoxicity in sensitive varieties of grapes. To serve as an effective fungicide and miticide, and to avoid plant injury, sulfur dioxide levels following a sulfur application are likely to be in the range of 0.1 to 0.5 parts per million in the field for a sustained period. You might ask, since sulfur dioxide is a hazardous gas, how is it possible to avoid having it drift or diffuse into areas surrounding sulfur-treated fields? You can't. It's a gas. And as pesticide applicators, we are supposed to control drift from our application sites. We are supposed to avoid having our pesticide sprays, our pesticide applications drift onto others' properties, onto others' persons. But in the case of sulfur, that is an impossibility. A group of researchers from the University of California, Berkeley, published a study in Environmental Health Perspectives This study, they looked at children and they followed these children for over a decade. And they correlated the distance they lived from application sites with the amount of medications they needed for respiratory illnesses like asthma and from distressed lung function. They found a strong correlation between agricultural sulfur applications and respiratory distress in children living within 1 kilometer of application sites. There is no way that anybody applying sulfur as a micronized spray in a solution or as a dust are going to be affecting people living a kilometer away, unless it's a gas. And it is a gas. That's how sulfur works. Beyond 3 kilometers, they found no significant associations with sulfur applications. And sulfur dioxide can account for every symptom they found in the children living within that 1 kilometer block. Nothing else can. Based upon publications from numerous government safety institutions and agencies, these children had to be exposed to intermittent levels of sulfur dioxide in the range of 0.1 to 0.5 parts per million of sulfur dioxide in order to have caused the symptoms seen in this experiment, in this study following these children. And if sulfur dioxide concentrations are reaching levels of 0.1 to 0.5 parts per million up to a kilometer from application sites, how far from application sites might we expect to see reduced fertility? Something that wasn't studied. That's only 0.015 parts per million. Or how far from these sites might we see an increase in miscarriages and congenital birth defects? Those studies show even lower concentrations are correlated with those, even down to 1 part per billion. Such studies looking for correlations between sulfur dioxide generated at agricultural sites and health effects in the community are non-existent, other than this one study that correlates sulfur applications with lung distress in children. Using a simple gas diffusion model, and knowing that we are seeing parts per million of sulfur dioxide up to 0.5 parts per million, likely up to a kilometer from application sites, we can calculate at what distance we might see these lower parts per million that are attributable to reduced fertility and birth abnormalities and miscarriages, etc. And in doing so, we can see that up to 5.77 kilometers from application sites, we might see rates of sulfur dioxide that could be reducing fertility in these areas. and up to 22.36 kilometers from these application sites, there could be problems with, associated that you wouldn't want pregnant women exposed to. Do these findings of the California Prop 65 report on sulfur dioxide really translate into the field? If they do, there's a problem. The thing is, we just don't know. This is a problem. Sulfur pesticides bear caution signal words, are approved for organic food production, and list the active ingredient as sulfur with all the minimal hazards of sulfur. But this sulfur is actually controlled release sulfur dioxide. And sulfur dioxide, when used as a pesticide, those products bear a danger signal word with the skull and crossbones. And they're true poisons with reproductive hazards documented by California in Prop 65. And get this, sulfur is the most widely used agricultural pesticides, both in terms of amount applied and acreage applied to. In 2022, 39 million pounds were applied in California. Add a couple of oxygens to that, and you're up to 80 million pounds of sulfur dioxide potentially generated. Agriculture is now the largest human-made source of sulfur dioxide to the environment, primarily due to the widespread use of elemental sulfur as a pesticide and as a soil amendment. Even sulfur that is applied to the soil, some of that will get converted into sulfur dioxide as well, though not nearly as much. As a horticulturist, I know that if you're using sulfur as a soil amendment to, say, lower the pH of soils, you incorporate it into the soil so you get good biological activity oxidizing it into sulfur dioxide and sulfate to sulfate, which is the form that plants take up. If you sprinkle sulfur over the top of the soil, you're not going to get the acidification. This is well known in horticulture because if you sprinkle it over the surface, it gases off, it vaporizes. So, we have so much evidence pointing to sulfur sublimating to sulfur dioxide. It's unquestionable. This is what is happening. Good alternatives to sulfur are out there. My company isn't the only one that has good alternatives to sulfur. We've had a product that has beaten sulfur in every field trial done by a university in controlling, say, powder and mildew, and at rates that are cost effective. It is time to reduce our sulfur use.